Hold this thought for a moment, that sleek smartphone in your hand, buzzing with the latest notifications, packed with more computing power than the spaceship that first took humans to the moon. Now picture this, a 2,000-year-old artifact, maybe a carved stone tablet or an ancient manuscript, lying silently in a museum. At first glance, they couldn't be more different. One feels like the pinnacle of modern innovation, the other a relic of a distant past. But what if I told you the lines between them aren't as clear as they seem? That ancient civilizations, centuries or even millennia ago, might have envisioned or even predicted the very technologies we take for granted today. It sounds like something out of science fiction, but history is full of eerie foreshadowing. From intricate clockwork mechanisms in ancient Greece that mirrored modern computers, to visionary descriptions of flying machines in Sanskrit texts that read like blueprints for helicopters, our ancestors left behind clues that border on the prophetic. These weren't just lucky guesses or vague metaphors. Some of these ideas were so precise, so shockingly detailed, they force us to ask, how could they possibly have known? Were they tapping into lost knowledge, or did humanity's imagination somehow leap across time, planting seeds for the future? That's the mystery we're unraveling today. Over the next 25 examples, we'll journey through time, from the dusty libraries of Alexandria to the towering temples of Mesoamerica, uncovering moments where the ancient world seemed to peer into our modern reality. You'll see inventions that defy their era, prophecies that came true with unsettling accuracy, and designs so advanced they still baffle historians. This isn't just about admiring the past, it's about discovering how interconnected human ingenuity really is, how a spark of thought from thousands of years ago might have lit the path to the world we live in now. So let's step into the shadows of history, where the line between ancient wisdom and modern marvels starts to blur. The first stop on our journey takes us to the sun-drenched waters off the coast of Greece, where sponge divers in the year 1900 made a discovery that would rewrite history. They stumbled upon a shipwreck near the island of Antikythera, packed with statues, jewelry, and pottery, typical treasures from the ancient world. But one object stood out, a lump of corroded bronze about the size of a shoebox, its secrets hidden beneath centuries of decay. At first glance, it seemed unremarkable, but when researchers painstakingly cleaned and examined it, they uncovered something astonishing: an intricate network of interlocking gears, dials, and inscriptions, precision engineered with a complexity unmatched for its time. This was the Antikythera Mechanism, a 2,000-year-old device so advanced it wouldn't be rivaled again until the mechanical clocks of the 14th century. Imagine a hand-cranked machine that could predict solar eclipses, track the cycles of the Olympic Games, and chart the positions of the 5 known planets with pinpoint accuracy. Its gears moved in perfect harmony, simulating the irregular motions of the moon and even accounting for subtle gravitational wobbles in its orbit, a feat of engineering that wouldn't be understood again until Isaac Newton's laws of motion over a millennium later. What makes this device truly mind-bending is how it mirrors modern computing principles. The Antikythera Mechanism wasn't just a clock or calendar, it was a programmable analog computer. Users could input a date, and its gears would calculate celestial events far into the future or past. It's as if the ancient Greeks had built a tiny, mechanical universe inside a box, centuries before the scientific revolution. Scholars still debate who could have designed it, perhaps Hipparchus, the father of trigonometry, or Archimedes, whose lost works hinted at similar inventions. But here's the haunting question: how many other devices like this were lost to time? The Antikythera Mechanism survived only by chance, resting silently on the ocean floor while the knowledge to recreate it vanished. It forces us to wonder, was this an outlier or a glimpse of a much more technologically sophisticated ancient world than we've dared to imagine? Now, let's shift our gaze from the gears of ancient Greece to the deserts of Mesopotamia, where another artifact challenges everything we thought we knew about technological progress. In the basement of Baghdad's National Museum sit a handful of unassuming clay jars, roughly the size of a fist, dating back to the Parthian or Sasanian period around 2,000 years ago. At first glance, they look like ordinary pottery, but inside each one, archaeologists found something extraordinary: a copper cylinder carefully sealed with asphalt, housing an iron rod at its core. These objects, known as the Baghdad Batteries, have sparked fierce debate for decades. When filled with an acidic or alkaline liquid like vinegar or grape juice, they produce a small but measurable electric current. The setup is eerily similar to a modern galvanic cell, the basic principle behind batteries. In fact, experiments with replicas have shown they could generate around 1 to 2 volts of electricity. That's not enough to power a light bulb, but it's enough to electroplate objects, adding a thin layer of gold or silver to jewelry or decorative items. And here's where things get even more intriguing. Ancient Mesopotamian texts describe a process called gilding, where objects were coated in precious metals using mysterious techniques. Could these jars have been the secret behind their craftsmanship? Some scholars think so, pointing to artifacts from the region with gold plating too fine to have been hammered on by hand. Others remain skeptical, arguing the jars might have held sacred scrolls or served a purely ceremonial purpose. But even if their exact use remains a mystery, the implications are staggering. If these were indeed primitive batteries, it means the concept of electricity wasn't just a modern breakthrough. It was toyed with, perhaps even harnessed in the ancient world. That idea rewrites the narrative of scientific discovery, suggesting a thread of knowledge that flickered in and out of history long before Galvani and Volta sparked the electrical age in the 18th century. What's even more fascinating is how these ancient inventors might have stumbled upon the idea. Unlike the Greeks, who worked with precise calculations, the Baghdad batteries hint at trial and error, an accidental discovery, perhaps, that copper, iron, and citrus juice could create a tingling sensation or a faint spark. Did they grasp the full potential of what they'd found? Probably not. But like so many lost innovations, it's a reminder that human curiosity has always pushed boundaries, even when the tools to fully understand them lay centuries away. And that's the haunting beauty of artifacts like these. They don't just fill gaps in history, they tear open new questions. How many other experiments with electricity might have vanished without a trace? Were these jars a one-off curiosity, or the last surviving fragments of a wider, forgotten tradition? Every time we dig into the past, we're left wondering just how close or how far our ancestors really were from the world we know today. Picture this, a bustling marketplace in 1st century Alexandria, where merchants haggle over spices and scholars debate under the towering library's shadow. Amid this hive of activity, an inventor named Hero unveils a device that seems plucked from a dream. A bronze sphere perched on a stand, hissing steam from 2 curved nozzles. When heated, it begins to spin faster and faster until it becomes a blur of motion, powered by nothing but boiling water. This was the Eolipile, the world's first known steam engine, an invention so ahead of its time it wouldn't find its true purpose until the Industrial Revolution 1700 years later. Hero's device was deceptively simple in design but revolutionary in concept. The sphere, filled with water, was mounted on a central axis with hollow pipes feeding steam into it. As the water boiled, steam shot out through the nozzles, creating thrust, the same basic principle that would one day drive steam turbines and even early jet engines. The Eolipile wasn't just a curiosity, it was a working demonstration of Newton's third law of motion. For every action, there's an equal and opposite reaction, though Hero couldn't have known it at the time. What's even more astonishing is how Hero envisioned using this technology. In his writings, he described automated temple doors that appeared to open by divine will, actually powered by hidden steam mechanisms. He designed mechanical puppets that danced when heated, and even a self-refilling wine bowl using hydraulic pressure. These weren't just toys, they were blueprints for automation, hinting at a world where machines could perform tasks without human muscle. Yet here's the twist: Hero's steam engine never sparked an industrial revolution in ancient times. While his designs were brilliant, they remained novelties, perhaps because slave labor was abundant, or because the underlying science wasn't yet understood enough to scale up. It's as if the ancient world had all the pieces but couldn't see the full puzzle. When James Watt perfected the steam engine in the 18th century, he wasn't building on Hero's work. He was reinventing it from scratch, unaware that the seed had been planted centuries earlier. This raises a haunting question: how many other leaps forward might have been lost in time? Hero's manuscript survived by chance, copied and recopied by scribes over generations. What other ideas faded into obscurity? The Eolipile stands as a stark reminder that innovation isn't always linear. Sometimes the future arrives too early, only to retreat into the shadows, waiting to be rediscovered. And perhaps that's the most fascinating lesson here. Hero's engine wasn't just a precursor to modern technology. It was proof that human creativity knows no bounds, even when the world isn't ready to catch up. The same fire that boiled water in his bronze sphere would one day power locomotives and factories, but for him, it was enough to make the impossible spin before an audience's astonished eyes. In that moment, the line between ancient ingenuity and modern marvels didn't just blur, it vanished entirely. Deep in the crypts of Egypt's Temple of Hathor at Dendera, a series of strange carvings crawl across the ancient stone walls. To the untrained eye, they might look like typical religious symbols: snakes coiled inside elongated pods, their tails trailing into lotus flowers. But to some modern observers, these images spark an electrifying possibility. Could they depict advanced technology? Specifically, could they be ancient blueprints for electric light bulbs? The so-called Dendera Light has become one of Egyptology's most heated debates. At the center of the controversy is a single, haunting relief. A human figure holds what appears to be a giant, bulbous object, inside which a serpent extends like a glowing filament. Wires seem to connect it to a box gripped by a kneeling figure, almost like an engineer operating a power source. To supporters of the ancient electricity theory, this isn't just art. It's a technical diagram, a 2,000-year-old representation of a Crookes tube or an early arc lamp predating Edison's invention by millennia. Skeptics, of course, have a different take. Mainstream Egyptologists argue these carvings are classic representations of the Djed pillar, a symbol of stability intertwined with the sun snake, a mythological creature linked to creation myths. The filament might simply be the god Harsomptus emerging from a lotus, a spiritual metaphor, not a technical schematic, and the wires, likely stylized lotus stems common in temple iconography. After all, if the Egyptians had electric lights, where are the remnants of generators, wires, or even mentions of such technology in their meticulous records? But here's where things get fascinating. When engineers reconstructed the Dendera design based on the light bulb interpretation, they found something startling. The proportions and shape of the bulb resemble a type of mercury vapor tube capable of producing a faint glow when electrified. The serpent aligns eerily with the behavior of plasma filaments in such devices, and the box could theoretically function as a crude battery or capacitor, not unlike the Baghdad artifacts we discussed earlier. The temple's location adds another layer of mystery. Dendera's underground chambers are pitch black, yet their walls are covered in intricate carvings, work that would have required consistent, bright lighting. Torches would have blackened the ceilings with soot, and oil lamps would have left residue, yet there's no evidence of either. Could there have been another light source now lost to time? The truth likely lies somewhere in the middle. The carvings probably weren't literal blueprints for light bulbs, but they might reflect a deeper intuition about energy and illumination. Ancient priests often used symbolic language to describe cosmic forces, and electricity, with its invisible power and sudden flashes, would have seemed divine. Maybe the Dendera reliefs capture a sacred understanding of light's nature, filtered through the lens of ritual. Or maybe, just maybe, there's a sliver of forgotten knowledge embedded in those stone walls. Either way, the Dendera Light forces us to ask how much of our modern understanding is truly new, and how much is simply rediscovery, whispered across the centuries in symbols we're still learning to decode. Imagine a naval battle in the year 678, where the fate of an empire hangs in the balance. The Byzantine fleet, vastly outnumbered by Arab invaders, seems destined for defeat until crews unleash a nightmarish weapon unlike anything the world had seen. From pressurized bronze tubes mounted on their ships, they spew a liquid hellfire that clings to the waves, igniting enemy vessels in an unstoppable inferno. Water only makes it burn fiercer. Screaming sailors leap into the sea, only to find the flames pursuing them like a living thing. This was Greek fire, the ancient world's closest equivalent to a flamethrower, and one of history's most devastating lost technologies. The secret of Greek fire wasn't just its terrifying effects, it was the science behind it. Descriptions from Byzantine texts suggest a substance eerily similar to modern napalm or thermite, capable of spontaneous combustion when exposed to air or water. Some accounts mention it being launched in clay grenades or sprayed through siphon pumps with a deafening roar, creating firestorms that could reduce entire fleets to ash. What made it truly revolutionary was its tactical precision. Unlike traditional fire arrows or pitch pots, Greek fire could be directed like a liquid whip, controlled by trained operators who adjusted valves and nozzles, an ancient precursor to the flamethrower units of 20th century warfare. But here's where the mystery deepens. The exact recipe for Greek fire was so closely guarded that it vanished with the fall of Constantinople in the 13th century. Byzantine emperors reportedly stored the formula in a vault, sharing it only with a single trusted chemist and his heirs. Modern scientists have tried for centuries to recreate it, proposing ingredients from quicklime and naphtha to petroleum and pine resin. Some theories even suggest the Byzantines stumbled upon an early form of chemical warfare, adding sulfur or saltpeter to create toxic fumes alongside the flames. What's striking isn't just the weapon itself, but how its strategic use mirrors modern military thinking. Greek fire wasn't just a tool of destruction, it was psychological warfare. The mere sight of it could rout enemy forces, much like the terror inspired by napalm in Vietnam or white phosphorus in modern conflicts. The Byzantines understood the power of controlling fire both physically and symbolically centuries before combustion became the engine of industry. And that's the haunting legacy of Greek fire. It represents a technological peak that slipped through history's fingers. Imagine if that knowledge had survived, how might it have reshaped the medieval world? Would we have seen flamethrowers in the Crusades or early chemical engines powered by its principles? The loss of its recipe isn't just a historical footnote, it's a reminder of how fragile progress can be and how many breakthroughs might have flickered out, leaving only shadows on the walls of time. Standing on the shores of Italy today, 2,000 years after they were built, the ancient Roman harbors still defy the sea. While modern concrete structures crumble in decades under saltwater's assault, piers and breakwaters from Augustus' reign remain intact, almost petrified by time. What's their secret? A recipe lost for centuries, rediscovered only recently, revealing that Roman engineers didn't just build infrastructure, they gave it the power to heal itself. The magic lies in a seemingly flawed ingredient, lime clasts. For years, scientists assumed these tiny white chunks scattered through Roman concrete were sloppy mixing, a sign of primitive methods. But advanced imaging techniques unveiled the truth. Those imperfections were actually microscopic time capsules of reactive lime designed to crack open when seawater seeped in. As fractures form, the clasts dissolve, releasing a calcium-rich solution that recrystallizes into new binding material, essentially growing fresh mortar to seal gaps. It's a biological-like process, mirroring how human bones mend after a break. Modern concrete, by contrast, fights a losing battle against erosion. Our mixes rely heavily on Portland cement, which forms rigid structures vulnerable to tiny cracks that spread like spiderwebs. Once water penetrates, corrosion accelerates, requiring costly repairs. The Roman approach flips this weakness into strength. Their concrete wasn't just durable, it thrived in seawater, growing stronger through chemical reactions with salt. Marine analyses show harbors like Portus Cossanus developed rare minerals like aluminous tobermorite over centuries, reinforcing their structure like geological armor. Perhaps the most astonishing detail is how intentional this was. Roman texts describe volcanic ash from Pozzuoli being shipped across the empire specifically for marine projects. When mixed with lime and seawater, this ash created a pozzolanic reaction, a molecular handshake forming compounds modern labs struggle to replicate. Recent mining studies even suggest Romans mixed their concrete, combining quicklime with water at high temperatures to generate self-healing pockets intentionally. The implications are staggering. Today, infrastructure repairs consume billions annually, while Roman ruins mock our ephemeral solutions. Imagine bridges that patch their own potholes or subway tunnels that regenerate as they age. This isn't science fiction, it's buried knowledge waiting in plain sight. Researchers are now racing to reverse engineer these principles, blending ancient wisdom with nano-engineering. Early trials adding synthetic lime clasts to modern mixes show promise, with microcracks sealing in under 2 weeks. Yet the deeper question lingers: how did Romans grasp concepts we're only now uncovering with electron microscopes? Their concrete wasn't just a material, it was a philosophy, treating time as an ally rather than an enemy. In an era without molecular science, they engineered resilience into stone itself, leaving behind monuments that whisper secrets we've yet to fully decipher. In the year 138, a strange scene unfolded in the imperial court of China's Han Dynasty. A dragon-headed mechanism mounted on a bronze urn suddenly clattered to life, one of its 8 sculpted toads catching a ball dropped from the dragon's jaws. To the uninitiated, it might have seemed like an elaborate automaton, a royal plaything. But this device had just performed something extraordinary, detecting an earthquake over 300 miles away, days before messengers arrived with news of the devastation. This was Zhang Heng's seismoscope, a 2,000-year-old masterpiece of engineering that anticipated modern seismology by nearly 2 millennia. What made this invention so remarkable wasn't just its accuracy, it was the sheer elegance of its design. The urn, standing about 6 feet tall, housed an inverted pendulum hidden inside its ornate exterior. When tremors struck, the pendulum swayed, activating a series of levers that released a single bronze ball from one of 8 dragon mouths, each corresponding to a cardinal direction. The ball would then land in the mouth of a waiting brass toad below, pinpointing the quake's origin with startling precision. Historical records describe it detecting earthquakes the court hadn't even felt, earning Zhang Heng a claim as the man who could sense the unseen. Modern engineers have spent decades trying to reverse engineer the seismoscope's mechanics. Some theories suggest it used a delicately balanced central column that toppled like a domino at the slightest tremor, while others propose a suspended weight that rolled along grooved tracks. What's undeniable is its sophistication. It didn't just sense vibrations, it filtered out local disturbances like passing carts or footsteps, responding only to the low-frequency waves of distant quakes. This level of discrimination wouldn't be matched until the invention of electromagnetic seismographs in the 19th century. But here's the real marvel. Zhang Heng built this without any understanding of plate tectonics or seismic waves. He worked purely from observation, likely noting how jars of water rippled before quakes or how hanging objects swayed unpredictably. His genius was in translating these subtle clues into a functional system, wrapping it in artistry to make the invisible visible. The dragons and toads weren't just decoration, they transformed raw data into a spectacle, ensuring even emperors could grasp the Earth's restlessness. Today, replicas of the seismoscope have been tested with surprising results. In 2008, researchers at the Chinese Academy of Sciences built a model that successfully detected simulated quakes, proving the concept wasn't just legend. Yet the original device's fate remains a mystery. Like so many ancient wonders, it vanished into time, leaving only descriptions etched into history. Zhang Heng's invention forces us to reconsider how we measure progress. Was his seismoscope merely a precursor to modern tools, or something far more profound, a testament to human intuition's power to bridge gaps in knowledge? In an age without microscopes or mathematics to explain the Earth's movements, he crafted a machine that didn't just predict disasters, it whispered back to the planet itself. High above the rainforests of Central America, where the branches of ceiba trees brushed against the stars, Mayan astronomers charted the heavens with a precision that still leaves modern scientists speechless. Their observatories weren't domed buildings with telescopes, but open-air temples with sightlines carved into stone windows and doorways aligned so precisely that they functioned like celestial crosshairs. At El Caracol in Chichen Itza, a spiral tower's narrow slits framed Venus at its most extreme positions in the sky, while the pyramid of Kukulkan at the spring equinox cast a shadow that slithered like a serpent down its steps. These weren't just architectural marvels, they were living calculators, stone equations that tracked time itself. What's truly staggering is the accuracy they achieved without a single metal tool or written numeral system. The Mayans calculated the solar year at 365.2420 days, only 17 seconds shorter than our modern measurement. Their Venus cycle, spanning 584 days, matches today's astronomy down to a 2-hour margin over 500 years. They even accounted for the gradual shift in Earth's rotation, a phenomenon called precession that wasn't formally documented until the Renaissance. How? By compiling records spanning generations, noting patterns in bark paper codices now lost to time, save for a handful that survived the Spanish conquest. Consider the Dresden Codex, a battered manuscript that survived centuries in European libraries before scholars realized its significance. Inside its fragile pages lies a table tracking Venus's movements across 8 years, predicting its appearances as both the morning and evening star with eerie precision. But here's the twist: the Mayans didn't just observe Venus, they feared it. To them, the planet was Kukulkan's fiery twin, a harbinger of war. Their calculations weren't abstract science, they were survival tactics, allowing rulers to time battles or plant crops based on celestial omens. Their eclipse predictions border on the supernatural. Using a complex system of overlapping cycles called the calendar round and long count, Mayan scribes could forecast lunar eclipses within a day over spans of 33 years. At Capon, a stairway inscription details an eclipse in July 653, verified by NAS, a retro calculations to have been visible there, the real shock. The Mayans nailed the timing despite believing eclipses were celestial monsters devouring the sun, not the mechanical dance of orbiting bodies. The most haunting question isn't how they achieved this accuracy, but why their knowledge didn't spark a global scientific revolution. While Europe fumbled through the Dark Ages, Mayan thinkers had essentially invented modular arithmetic to reconcile their multiple calendars. Their number system, with its placeholder 0, could express values into the millions, concepts that wouldn't reach the old world for centuries. Perhaps the answer lies in their worldview. To them, time wasn't a straight line but a sacred wheel turning eternally. Their genius wasn't in predicting the future, but in revealing how deeply the past already knew it. Standing in the ruins of Tikal today, where temples align with the solstice sun, you can almost hear the whispers of those astronomer priests. They didn't just track the stars, they wove time into tapestries of stone and starlight, proving that precision isn't just the domain of silicon and steel. Sometimes it's etched in the shadows of pyramids, waiting centuries for us to look up and understand. There's a passage in the ancient Sanskrit epic, the Mahabharata, that reads less like mythology and more like an aerospace manual. It describes a Vimana, a celestial chariot, with wheels that retract, wings that adjust to wind currents, and a propulsion system roaring like thunder. Another text, the Samaranganasa Tradhara, details even stranger specifics: mercury-filled engines, spinning gyroscopes, and alloys that could withstand extreme heat. To modern eyes, these descriptions sound uncannily like advanced aircraft, complete with mechanical systems far beyond what we'd expect from a civilization that flourished over 2,000 years ago. The controversy surrounding Vimanas hinges on this eerie precision. Ancient Indian texts classify them into multiple types, some for interplanetary travel, others for stealth missions, even weather-controlled variants. The Vimana Shastra, a controversial early 20th century manuscript claiming to be based on lost Vedas, goes further, illustrating blueprints with layered wings, electromagnetic propulsion, and energy shields. Skeptics dismiss it as a hoax or poetic metaphor, but the sheer consistency across unrelated texts raises questions. How could multiple authors, separated by centuries, all imagine flying machines with such technical coherence unless they were recording something beyond mere myth? Modern aerospace engineers have added fuel to the debate. When researchers at the Indian Institute of Science attempted to model a Vimana based on the Vimana Shastra's descriptions, they found some elements shockingly viable. The Mercury vortex engine, for instance, mirrors theoretical concepts for ion propulsion, while the described lenticular, disc-shaped designs align eerily with modern UFO sightings. Even the materials mentioned, a mysterious alloy called Tamagarbhaloha, bear similarities to titanium composites used in stealth aircraft today, yet the most compelling link might be cultural. Ancient Indian rulers like King Ashoka allegedly maintained Vimana vaults, guarded libraries of aerospace knowledge, while Jain texts speak of ancient sages who taught flight mechanics to humanity. These accounts blur the line between legend and lost technology, especially when paired with global parallels like Ezekiel's wheel in the Bible or the flying fire ships of Chinese lore. Were Vimanas purely symbolic, or could they represent fragmented memories of a forgotten technological epoch? The answer might lie in how we interpret flight. Vimanas weren't just machines, they were vessels of the gods, often described as shifting between dimensions or powered by mantras, sound frequencies. This spiritual layer complicates things. Could these texts be encoding advanced physics in religious terms, much like alchemy disguised early chemistry? The Mercury engines, for example, might symbolize quantum states, while wind-guided wings could hint at anti-gravity principles we're still unraveling. What's undeniable is how these ancient ideas resonate today. When the U.S. military declassified reports of UFOs exhibiting instantaneous acceleration and anti-aerodynamic movement, the parallels to Vimana capabilities sparked a frenzy among researchers. It's as if the past and present are locked in a dialogue, separated by millennia but connected by a shared vision of flight beyond our current understanding. Whether Vimanas were real aircraft or prophetic imagination, their legacy challenges the timeline of human innovation. They force us to ask, did ancient cultures witness or even create technologies we're only now rediscovering? And if so, how many other myths might be waiting for science to catch up? The siege of Syracuse in 212 BC wasn't just a military conflict, it was a clash between brute force and one man's genius. As Roman galleys closed in on the Sicilian coast, the aging mathematician Archimedes supposedly unveiled a weapon so audacious it bordered on myth. According to ancient accounts, he arranged a series of polished bronze shields along the waterfront, angling them to focus sunlight into a searing beam that set enemy ships ablaze. The stories claim flames erupted instantly, sails bursting into fireballs before the terrified crews could react. This legendary death ray has been debated for centuries. Was it an actual feat of engineering or just a tale inflated by time? Modern scientists have put the death ray to the test with surprising results. In 2005, a team from MIT attempted to recreate Archimedes' weapon using 127 mirrored panels roughly the size of ancient shields. On a clear Boston afternoon, they focused sunlight onto a wooden ship replica 200 feet away. Within minutes, smoke curled from the hull, and at the 10-minute mark, flames erupted. The experiment proved the concept was physically possible, though skeptics argue that Syracuse's hazy Mediterranean skies and the Roman fleet's constant movement would have made real-world application far trickier. The parallels to modern directed energy weapons are impossible to ignore. Today's military lasers, like the U.S. Navy's LWS system, operate on similar principles, concentrating beams to melt drones or disable missiles. Archimedes' death ray might have been a primitive ancestor, but the core idea remains unchanged, harnessing light itself as a weapon. Even the limitations match up. Just as clouds could disrupt his mirrors, modern laser effectiveness drops in fog or rain. What makes this story truly fascinating isn't just the technology, it's the mind behind it. Archimedes was already revolutionizing mathematics with his work on pi and hydrostatics. His understanding of parabolic reflectors, evidenced in writings like On Burning Mirrors, suggests he grasped optics well enough to design such a system. But here's the twist: no contemporaneous Roman accounts mention the death ray. The earliest references come centuries later from authors like Lucian and Galen, leaving historians divided. Was it omitted because it seemed too fantastical, or because it never existed outside legend? The debate reflects a deeper tension in how we view ancient innovation. Part of us wants the death ray to be real, to believe a lone genius could outwit an empire with sheer intellect. Yet even if the mirrors never burned a single ship, their legacy persists. Solar furnaces in modern France and California now use the same principles to generate clean energy, proving that Archimedes' vision, whether fact or fable, still illuminates our path forward. The line between myth and breakthrough might be thinner than we think. From the scorching deserts of southern Peru, the Nazca Lines stretch across nearly 200 square miles of arid plateau, massive geoglyphs so enormous they can only be fully appreciated from the air. Etched into the earth between 500 BC and 500 AD, these precise formations depict spiders, hummingbirds, monkeys, and geometric patterns, some stretching over 1,200 feet long with lines straighter than modern laser measurements. But here's the unsettling question: if these designs were meant to be seen from above in an era before human flight, who or what were they signaling? One controversial theory suggests these weren't just sacred art, but functional markers, ancient runways or landing strips for aerial vehicles. Proponents point to the uncanny resemblance between Nazca's long, flat trapezoids and modern airport taxiways. The geoglyphs crushed rock surfaces which repel wind erosion and resist heat absorption, eerily mirror the properties of concrete used in contemporary airstrips. Even stranger, some formations align with solstice sunrises and underground water sources, hinting at a navigational purpose beyond mere decoration. Skeptics, of course, dismiss the ancient airport idea as pseudoscience. They argue the lines were ritual pathways for processions, aligned with celestial events to communicate with deities. Yet even this explanation raises puzzles. Why would processional routes require such inhuman precision, visible only from altitudes exceeding 600 feet? the straightest Nazca lines deviate less than 1 degree over miles, a feat requiring advanced surveying knowledge. And why do certain formations, like the so-called launch platform, resemble technical diagrams more than religious symbols? Intriguingly, modern pilots report unusual electromagnetic anomalies over the lines, with compass needles spinning unpredictably. This has led some researchers to speculate about mineral deposits beneath the glyphs, possibly used as natural beacons for aircraft relying on magnetic guidance. Ancient astronaut theories take it further, suggesting the Nazca people collaborated with or witnessed extraterrestrial visitors who needed these markings for navigation. But before we dismiss this as fantasy, consider a middle ground. Could the lines represent an encoded understanding of aerial perspective, a way to bridge the earthly and the divine? The most compelling evidence might lie in comparative archaeology. Similar giant geoglyphs exist worldwide, from Australia's Aboriginal marvels of the sand to the Middle East's wheel-shaped kites, often in areas with legends of sky gods. Whether functional or symbolic, these colossal artworks reveal a universal human impulse to communicate with the heavens. The Nazca lines challenge us to reconsider not just ancient technology, but ancient imagination. What did they know about flight that we've forgotten? And if these were indeed runways, what magnificent vessels once touched down on them, leaving no trace but whispers in the dust? High in the Andes, where mist curls around the peaks like ghostly fingers, the walls of Sacsayhuaman stand as a monument to architectural mastery that defies logic. These fortress walls, built by the Inca around the 15th century, are assembled from stones so precisely cut that not even a razor blade can slip between them. The largest blocks weigh over 100 tons, yet they fit together in a dizzying, three-dimensional jigsaw puzzle, interlocking without a speck of mortar. No two stones are identical. Each is a unique shape, curved and angled to marry perfectly with its neighbors, like a colossal game of Tetris carved in granite. What's baffling isn't just the precision, it's the apparent lack of tools capable of such work. The Inca had no iron, no wheeled transport, and no written language to blueprint these designs. Modern engineers struggle to explain how they achieved these seamless joins with only bronze chisels and stone hammers. The surfaces are so smooth they appear polished, yet tool marks are eerily absent. Some corners are rounded with radii so consistent they suggest the use of templates or guiding instruments we've yet to uncover. This has led to some spine-tingling theories. One hypothesis proposes the Inca possessed lost sonic or vibrational technology, perhaps using specific frequencies to soften stone temporarily, allowing them to mold it like clay. Spanish chronicles mention indigenous legends of liquefied rock, while local Quechua oral traditions speak of plants or herbs that could dissolve stone. Geologists point to a more earthly explanation. The Inca might have exploited natural fissures in the rock, patiently shaping blocks over years using abrasives like quartz sand. But even this doesn't fully account for the sheer geometric complexity. Then there's the puzzle of transportation. These megaliths were quarried miles away, across rugged terrain at altitudes that leave modern climbers gasping. How did they move 100-ton stones without beasts of burden or pulleys? Some researchers speculate about log rolling systems or inclined planes, but others note the absence of drag marks or crushed infrastructure. The Incas' own legends hint at another possibility, that the stones were awakened and guided into place by spiritual forces, a poetic nod to techniques we simply don't yet understand. The most haunting detail might be the walls' resilience. While Spanish conquistadors toppled Inca temples to build their colonial churches, Sacsayhuaman's walls endured centuries of earthquakes unscathed. Their interlocking design acts like a shock absorber, shifting minutely during tremors before settling back into perfect alignment. It's a principle modern architects call ashlar masonry, but the Inca executed it with a precision that rivals today's laser-cut materials. Standing before these walls today, you're left with a humbling thought. Perhaps the Inca weren't primitive at all, but masters of a forgotten science, one that blended physics, geology, and spirituality into something we're only beginning to glimpse. Their stonework isn't just a relic of the past, it's a silent challenge, daring us to unravel how hands without computers or steel could carve the earth itself into poetry. Hidden in the dim halls of the British Museum, a small greenish glass cup seems utterly unremarkable until light passes through it. Suddenly, the entire vessel transforms, glowing a deep, translucent red as if filled with wine. This is the Lycurgus cup, a 4th century Roman artifact that shouldn't exist. Crafted from dichroic glass, it changes color based on the angle of light, an effect that defies explanation until you realize the truth. Roman artisans were manipulating matter at the nanoscale over 1600 years before the term nanotechnology was even coined. The secret lies in the cup's composition. When scientists analyzed fragments under electron microscopes, they discovered something astonishing. The glass contains infinitesimal particles of gold and silver, each measuring about 70 nanometers across. That's roughly 1,000 times smaller than the width of a human hair. These nanoparticles interact with light in a process called plasmon resonance. When light hits them, electrons on their surfaces vibrate at specific frequencies, scattering certain wavelengths while absorbing others. The result, the glass shifts from jade green in reflected light to ruby red in transmitted light, a phenomenon modern labs struggle to replicate without precision equipment. What's truly mind-bending isn't just the effect, it's the intentionality behind it. Ancient texts like those by Pliny the Elder describe glassmakers adding finely ground metals to their melts, but until the Lycurgus cup's discovery, historians assumed this was alchemical superstition. Now we know better. Roman craftsmen weren't just tossing ingredients into a furnace, they were calibrating. The gold-to-silver ratio in the glass is meticulously balanced at roughly 3 parts silver to 1 part gold, a mix that maximizes the color-shifting properties. Even more remarkably, the particles are evenly dispersed, suggesting a controlled process like repeated heating and cooling to prevent clumping, an early form of thermal annealing. Modern material scientists have only recently unlocked similar techniques. NASA uses dichroic glass in advanced spacecraft sensors, while luxury car brands apply nanoparticle coatings to create iridescent paints. Yet the Romans achieved this with no understanding of atoms or light spectra. How? One theory points to their prolific use of gold leaf in murals and mosaics. Perhaps artisans noticed that when gold leaf scraps melted into glass during recycling, they created unusual colors. Through generations of trial and error, they might have refined the process into a repeatable, if not fully understood art. The Lycurgus cup isn't alone. Recent studies of other Roman glassware reveal similar nanoparticle inclusions, hinting at a broader tradition of nanoscale engineering. Some shards from Pompeii even show evidence of cadmium selenide quantum dots, crystalline structures used today in solar panels and medical imaging. This wasn't a one-off fluke, it was a sophisticated craft passed down through guilds and lost with Rome's fall. Standing before the cup today, you're left with a humbling realization. Our ancestors weren't just lucky. They were observant, patient innovators who manipulated their world with a precision we're only now beginning to measure. The line between ancient artistry and cutting-edge science isn't just blurred. It was never truly there to begin with. Imagine being a Viking navigator 1,000 years ago, steering your longship through the North Atlantic's endless gray, clouds heavy overhead, waves choppy beneath, no sun or stars to guide you for days. Yet somehow you know exactly where to go. How? According to ancient sagas, the answer lies in a magical tool called a sunstone, a crystal that could reveal the sun's position even when it was completely hidden. For centuries, historians dismissed these accounts as mere legend, until modern science proved them right. These sunstones weren't enchanted. they were sophisticated navigation tools harnessing the physics of polarized light. Made from calcite, cordierite, or tourmaline crystals, they worked by filtering scattered sunlight in the atmosphere. When held up and rotated, the crystal would darken or brighten depending on the angle of polarized light, allowing navigators to pinpoint the sun's location with eerie accuracy. Researchers have tested this method in real-world conditions, like a 2014 experiment where a team used a calcite sunstone under overcast skies and located the sun's position within 5 degrees. That's precise enough to navigate from Norway to Newfoundland without modern instruments. What's even more remarkable is how closely this mirrors modern optical technology. Today's aircraft and submarines use polarizing compasses based on the same principle, while satellite navigation systems like GPS indirectly rely on understanding light's behavior in the atmosphere. The Vikings didn't just stumble upon a neat trick, they tapped into a fundamental property of light that wouldn't be formally explained until the 19th century. But here's where the mystery deepens. Archaeological evidence for sunstones is scarce. Only a single calcite crystal found in a 16th century shipwreck off the Channel Islands has been tentatively linked to navigation. Some scholars argue the Vikings might have relied more on wave patterns, bird behavior, or wind direction, with sunstones reserved for the worst conditions. Others point to Norse sagas like the Rotholfsthottir, which describes King Olaf testing a sunstone by shading a navigator's head with a cloak and asking him to locate the sun. When the man correctly pointed through dense clouds, it wasn't magic, it was optics in action. The real question isn't just how sunstones worked, but how the Vikings conceptualized them. Without a theory of light polarization, did they see these crystals as divine gifts or tools of pure intuition? Their mastery of such technology hints at a culture deeply attuned to the natural world's hidden rhythms, where observation and myth intertwined. In a way, their sunstones were the earliest form of augmented reality, overlaying invisible data onto the visible world, centuries before screens or satellites. Now consider this: if the Vikings could navigate open oceans with a piece of crystal, what other forgotten technologies might still be buried in ancient texts or overlooked artifacts? Their sunstones don't just rewrite history, they remind us that innovation isn't always about creating something new. Sometimes it's about learning to see the old world in a brighter light. Buried beneath the sands of ancient Thebes, tucked inside the tomb of a temple priestess, archaeologists uncovered an object that shouldn't exist, a delicate wooden big toe, stained with age but still flexing at the joint. Known as the Cairo toe, this 3,000-year-old artifact isn't just a ceremonial piece. It's the world's oldest functional prosthetic limb, a masterpiece of early biomechanics that would make modern engineers nod in respect. What sets this prosthetic apart isn't just its age, it's the sophistication of its design. Carved from fine-grained sycamore and reinforced with linen cordage, the toe features a hinge that mimics the natural motion of a real joint. Where marks on the base plate show it wasn't just cosmetic, this toe was used daily, strapped to a living foot with leather laces. Researchers who replicated the device found it could support up to 80% of a person's body weight while walking, with the hinged joint reducing strain on the ankle. That's a level of ergonomic insight we'd expect from a modern orthopedic lab, not a workshop in the time of the pharaohs. The Cairo toe forces us to rethink ancient medicine's capabilities. Most prosthetics from antiquity were crude peg legs or hooks, designed more for symbolism than function. But this artifact suggests Egyptian healers understood weight distribution, mobility, and even the psychological importance of restoring natural movement. Texts from the era reference lifelike replacements for lost limbs, implying prosthetics were part of a broader medical philosophy, one that saw the body as a system to be repaired, not just mourned. Fast forward to today, and the principles behind the Cairo toe are shockingly relevant. Modern prosthetic limbs still prioritize 3 key elements the Egyptians nailed: articulation for movement, comfort through custom fitting, and durability under stress. The only difference, instead of sycamore and linen, we use carbon fiber and microprocessors. Even the psychological angle aligns. Contemporary studies show that patients adapt better to prosthetics that mimic natural motion, just as this toe's hinge would have eased its wearer's reintegration into daily life. But here's the real stunner: the Cairo toe might not be alone. A later Roman artifact, the Capua lega, a bronze prosthetic from 300 BC, features a hinged knee joint and sculpted musculature, suggesting a lineage of biomechanical innovation stretching across cultures. How widespread was this knowledge, and how much was lost when libraries like Alexandria burned? The Cairo toe is more than a medical curiosity. It's a fragment of a forgotten science, one that understood the body's engineering long before the term biomechanics existed. Standing in Cairo's Egyptian Museum today, staring at this tiny wooden toe, you're left with a humbling thought: maybe progress isn't always a straight line. Sometimes it's a footprint in the sand, one that shows how far ahead our ancestors really were. Long before the whirring of factory robots or the hum of artificial intelligence, the ancient Greeks were already dreaming of mechanical beings. In the smoky forges of Mount Olympus, the god Hephaestus crippled and cast out supposedly crafted golden handmaidens who moved with lifelike grace, tending his halls and even aiding him at the anvil. These weren't just poetic fantasies, they were detailed blueprints for a future humanity would spend millennia chasing. Take Philo of Byzantium's robot maid, described in his 3rd century BC treatise Pneumatics. This astonishing device, powered by water and steam, could mix wine and water in precise ratios, serving guests like an automated sommelier. Its inner workings, valves, levers, and counterweights mirror the logic of modern fluid dynamics and binary decision-making. When archaeologists recreated Philo's designs in 2014, they found the maid functioned flawlessly, its movements eerily reminiscent of today's industrial robotic arms. But the Greeks didn't stop at practical gadgets. Their myths brim with automata that blur the line between magic and engineering. Tolos, the bronze giant said to patrol Crete's shores, could heat his metal body red-hot to crush invaders, a terrifying precursor to thermal regulation systems in modern robotics. Then there's Pandora, molded from clay and imbued with life by the gods, embodying age-old anxieties about artificial consciousness that still haunt AI ethics debates today. What's striking isn't just the inventiveness of these ideas, but their conceptual sophistication. Aristotle pondered whether tools could one day work by themselves, while playwrights like Aristophanes staged comedies featuring self-navigating mechanical birds. Even the Antikythera Mechanism, with its intricate gears, hints at a culture obsessed with replicating life's rhythms in metal and steam. Yet the real mystery is why these innovations didn't spark an industrial revolution. Perhaps the answer lies in the Greek worldview. Their automata were divine crafts, not human inventions. Without a cultural framework to democratize technology, these marvels remained curiosities, whispers of a future just beyond their grasp. Standing in the shadow of Hephaestus myths today, we're left to wonder, were these stories just flights of fancy or fragmented memories of real technologies lost to time? Either way, they prove that the dream of artificial life didn't begin with silicon chips. It was forged in bronze centuries before the first spark of electricity. In the quiet hills of 9th century China, where Taoist monks sought the elixir of immortality, an accidental discovery would echo through the ages, changing the face of war, science, and even humanity's reach for the stars. These alchemists stirring cauldrons of exotic ingredients weren't just chasing myths. They were early chemists, meticulously recording their experiments in scrolls that survive to this day. One such text, the Wujing Zongyao, describes a volatile mixture of saltpeter, sulfur, and charcoal ingredients meant to purify metals or extend life. Instead, they created something far more transformative: gunpowder. The irony is palpable. A substance born from the quest for eternal life became one of history's most destructive forces. Yet the alchemists' notebooks reveal no sinister intent. Their trials were methodical, even poetic, testing ratios like artists blending pigments. Early recipes warned of mixtures that could frighten away evil spirits with noise and light, hinting at gunpowder's theatrical use in fireworks before its military potential was grasped. By the 10th century, however, Chinese generals had harnessed its power in fire arrows, bamboo tubes packed with the powder that launched themselves when ignited. These weren't just weapons, they were the ancestors of every rocket that would later pierce the atmosphere. What's often overlooked is how quickly gunpowder transcended warfare. The same monks who feared its explosive properties also pioneered controlled burning techniques, leading to advancements in mining, construction, and even early attempts at steam propulsion. A 13th century manuscript depicts a firewheel cart propelled by gunpowder charges, a crude but recognizable precursor to internal combustion. The alchemists' failed elixir had inadvertently unlocked the principle of controlled explosive force, a cornerstone of modern engineering. Centuries later, this knowledge would ripple across continents. When Mongol armies carried gunpowder westward, it sparked Europe's own technological renaissance, cannons reshaping castles into obsolete relics, muskets leveling feudal hierarchies. But the most poetic twist came in the 20th century, when scientists revisited those ancient powder ratios for an entirely new purpose: spaceflight. The same chemical reaction that once hurled stones at castle walls now fuels rockets carrying satellites, and someday perhaps humans, to Mars. Standing in a modern lab where engineers tweak solid rocket boosters with nanometer precision, it's humbling to trace this lineage back to a monk's smoky workshop. The alchemists sought to conquer death, but in their failure, they gave us something equally profound: the power to transform energy itself. Their legacy isn't just in the explosions that shaped history, but in the quiet truth that even accidents, when studied with curiosity, can light the way to the stars. Digging through the ruins of ancient Babylon, archaeologists uncovered clay tablets that seemed at first glance to be simple accounting records until they took a closer look. These weren't just lists of grain or livestock. They were complex mathematical texts featuring step-by-step solutions to problems we'd now recognize as quadratic equations. Dating back nearly 4,000 years, these tablets reveal a level of algebraic thinking so advanced it wouldn't be matched in Europe until the Renaissance. The most famous of these, known as Plimpton 322, reads like an ancient spreadsheet. It contains 15 rows of Pythagorean triples, sets of 3 whole numbers that perfectly fit the formula a 2 plus b2 equals c2, the foundation of geometry. But here's the shocker: the Babylonians weren't just memorizing these triples. They'd devised a systematic method to generate them, using algorithms strikingly similar to those in modern computer science. One tablet even outlines a procedure for solving what we'd call x2px equals q, complete with instructions like take half of p, square it, add q, a carbon copy of today's quadratic formula millennia before it was formally documented. What's truly revolutionary is how these methods mirror modern computation. The Babylonians didn't have symbolic algebra, no x's or y's, but their word-based algorithms functioned identically. Input values follow precise steps, output solutions. It's the same logic behind everything from Google's search algorithms to blockchain cryptography. Their tablets even include error-checking steps, verifying results by plugging them back into the original problem, a practice eerily reminiscent of debugging code. Consider the cryptographic angle. Some tablets describe reciprocal pairs, numbers that multiply to give one, a concept crucial to modern encryption like RSA. While they certainly weren't designing cybersecurity systems, Their mastery of multiplicative inverses hints at an intuitive grasp of relationships that underpin today's digital security. Why does this matter? Because it shatters the myth that algorithmic thinking began with Ada Lovelace or Alan Turing. The Babylonians were structuring problems computationally long before computers existed, treating math not just as theory but as a series of executable steps. Their work wasn't isolated genius either. Tablets show these methods were taught in scribble schools, passed down like software documentation across generations. Standing in a modern lab where algorithms shape every facet of life, it's humbling to realize how much we owe to 4,000-year-old clay. Those Babylonian scribes pressing stylus into wet mud weren't just doing math. They were writing the first lines of humanity's oldest program, one we're still running today. In the scorching deserts of ancient Persia, where summer temperatures could melt stone, engineers devised a method of cooling so effective it turned entire cities into oases of relief without a single watt of electricity. These were the wind catchers, towering chimney-like structures that rose above homes and bazaars, harnessing the slightest breeze to transform sweltering interiors into cool sanctuaries. Dating back as far as 3,000 years, these ingenious designs didn't just predate modern air conditioning, they surpassed it in elegance and sustainability. At first glance, a wind catcher seems simple, a tall, rectangular tower with openings at the top facing the prevailing wind, but the genius lies in the details. As hot air enters the tower, it's funneled downward through narrow internal channels, often passing over underground water reservoirs or moist clay walls. This contact cools the air through evaporation, dropping its temperature by as much as 20 degrees Fahrenheit before it spills into living spaces below. Meanwhile, the structure's shape creates a pressure differential, sucking stale indoor air upward and out through side vents. A natural ventilation system that refreshes rooms continuously. The sophistication goes deeper. Persian architects tailored wind catchers to local conditions. In Yazd, the city of wind catchers, towers were often multidirectional, capturing breezes from any angle. Coastal versions in Bushehr featured seawater channels for enhanced cooling, while desert designs incorporated subterranean ice chambers. Yes, ice in the desert by harvesting winter frost and insulating it beneath layers of straw and clay. The result was year-round climate control, all powered by physics alone. Modern architects are now rushing to relearn these ancient lessons. At the Masdar City project in Abu Dhabi, windcatcher-inspired towers reduce energy consumption by 40%. London's Kensington Oval Cricket Stadium uses a scaled-up version for passive cooling, while researchers at the University of Cambridge have modeled windcatcher physics to develop zero-energy cooling systems for refugee camps. Even NASA has studied the principles for potential use in Martian habitats, where energy-efficient temperature regulation will be critical. What's most humbling isn't just the technology's effectiveness, it's the philosophy behind it. Persian engineers didn't fight their environment, they collaborated with it, turning harsh winds and blistering heat into allies rather than adversaries. In an age of climate crisis, their approach feels less like a historical curiosity and more like a blueprint for survival. The wind catchers whisper a challenge across millennia. Progress isn't always about inventing something new. Sometimes it's about rediscovering what we've forgotten. For tens of thousands of years, Australia's Aboriginal peoples traversed the harshest landscapes on Earth without maps, compasses, or written language, yet they could navigate hundreds of miles with pinpoint accuracy. Their secret, songlines, intricate oral maps woven into music and story, encoding the continent's geography with a precision that rivals modern GPS. These weren't just melodies, they were living databases passed down through generations, embedding everything from waterhole locations to seasonal landmarks within rhythm and verse. Imagine a song that doesn't just tell a story but physically guides you. Each phrase corresponds to a specific stretch of land, a rock formation here, a bend in the river there. The tempo might slow near treacherous terrain, while chorus repetitions mark critical crossroads. In the central desert, Pitjantjatjara elders still demonstrate how a single song can lead travelers unerringly from Uluru to the coast, a journey of over 1,000 kilometers, with every hill and gully accounted for in verse. The land and the song aren't separate, they're mirrors of one another, a concept foreign to Western cartography but breathtakingly effective. Modern researchers have only recently grasped the sophistication of this system. When anthropologists compared songlines to satellite maps, they found uncanny correspondences, subtle lyrical cues aligning with nearly invisible paths, like animal tracks or star-guided shortcuts. Some songs even incorporate astronomical markers, linking terrestrial routes to constellations that shift with the seasons, creating a 4D navigation tool adaptable to changing conditions. It's as if Aboriginal cultures compressed an entire geographic information system into oral tradition, with no loss of fidelity across centuries, the most astonishing part. These songs weren't static. They evolved as the land did, with new verses added for shifted riverbeds or drought-altered grazing grounds. Unlike paper maps that fossilize a single moment, songlines were dynamic, updated in real time by those who sang them. This adaptability puts them closer to modern navigation apps than to medieval maps, a living, crowdsourced atlas sustained by memory and shared experience. What Western science calls dead reckoning, Aboriginal cultures understood as deep listening. They didn't just move through the land, they knew it in their bones, their songs carrying the pulse of the earth itself. In an age where we rely on satellites to find the nearest coffee shop, these ancient oral maps ask us a humbling question. How much have we gained in technology, and how much have we lost in truly knowing the world beneath our feet? Deep in the sweltering jungles of Mesoamerica, the Olmec civilization thrived over 3,000 years ago, long before rubber tires wrapped around wheels or rubber-soled shoes hit pavement. Yet nestled among their towering stone heads and jade artifacts lies an overlooked innovation, the world's first polymer scientists. These ancient innovators didn't just harvest rubber from the sap of local rubber trees. They engineered it, transforming sticky latex into bouncy balls, waterproof textiles, and even adhesive bindings that could glue stone to stone. This wasn't accidental discovery, it was systematic materials science, predating Charles Goodyear's vulcanization by a staggering 25 centuries. The process was deceptively simple yet chemically profound. Olmec artisans mixed fresh latex with juice from the morning glory vine, a plant they revered for its medicinal properties. Unbeknownst to them, the vine's sulfur-rich compounds acted as a natural vulcanizing agent, creating cross-links between latex molecules when heated over open flames. The result, rubber that retained elasticity without melting in the tropical heat or cracking in the cool of night. Modern lab tests confirm this mixture's durability. Some excavated rubber balls still rebound today, centuries after their creators vanished. But the Olmec didn't stop at toys. They applied their rubber mastery to everyday survival. Archaeologists have unearthed rubber-treated fabrics in Veracruz, woven into rain cloaks so effective they rival modern waterproof gear. Even more striking are the rubber-lined stone tools where adhesive bonds held blades firm through generations of use. The Aztecs later adopted these techniques, crafting rubber-soled sandals for long-distance messengers, an early precursor to athletic footwear. What's truly revolutionary is how this knowledge spread. By the time Spanish conquistadors arrived, rubber was a trade commodity across Mesoamerica, with specialized workshops in cities like El Menotti producing standardized rubber products. The material even played a spiritual role. Ritual ball games used rubber balls symbolic of the sun's movement, their bounce echoing celestial cycles. Today, chemists are re-examining Olmec methods for eco-friendly alternatives to synthetic rubber. Unlike petroleum-based production, their process was entirely sustainable, harvesting latex without killing trees and using organic additives. In labs from Amati to Tokyo, researchers now experiment with morning glory derivatives, seeking biodegradable rubbers inspired by ancient recipes. The Olmec's legacy stretches far beyond playgrounds or raincoats. They proved that material science isn't just a modern discipline, it's a human one, born from observation, experimentation, and the relentless drive to reshape nature's gifts. Their rubber balls didn't just defy gravity, they bounced ideas across millennia, waiting for us to catch up. Picture this: a patient lies still beneath the steady hands of a healer, their head carefully braced as a sharpened obsidian blade begins scraping away at their skull. No anesthesia, no sterile operating room, just methodical precision honed over generations. This wasn't some gruesome ritual, it was advanced neurosurgery performed over 7,000 years ago. From the highlands of Peru to the steppes of Siberia, archaeologists have unearthed hundreds of ancient skulls bearing the telltale marks of trepanation, deliberate holes drilled or scraped into living bone, often with evidence of healing that proves patients survived the ordeal. What's shocking isn't just the prevalence of this practice, it's the staggering success rate. Studies of Inca trep and skulls reveal survival rates as high as 80%, with some individuals undergoing multiple procedures over their lifetime. The techniques varied by culture. Peruvians used circular scraping motions with obsidian razors, while Bronze Age Europeans employed bow-driven drills eerily similar to modern surgical tools. Some Celtic specimens even show rectangular, hinged flaps cut into the skull, allowing bone segments to be lifted and replaced like little doors, a technique still used today to relieve brain swelling after trauma. The parallels to modern neurosurgery are uncanny. Ancient practitioners clearly understood critical boundaries, avoiding the midline sagittal sinus where a nick could cause fatal bleeding. Many holes align with areas we now know to be seizure foci or trauma sites, suggesting these weren't random acts but targeted interventions. The famed Hippocrates, writing in 4th century BC Greece, described trepanation for head injuries with clinical precision, noting how to distinguish between fractures requiring surgery and those that could heal naturally. His descriptions of lifting depressed bone mirror contemporary procedures for compound skull fractures. But here's the real mystery: how did they manage pain and infection? Archaeologists have found traces of coca leaves in Peruvian mummies, hair near trepanation sites, early local anesthesia, while Egyptian papyri reference honey and willow bark poultices, both now known to have antibacterial and anti-inflammatory properties. A Scythian skull from Crimea even shows bone growth around a silver plate implanted after surgery, suggesting some cultures experimented with biocompatible materials millennia before titanium mesh. The most haunting question isn't whether they could drill. It's why so many cultures independently arrived at the same solution. From Neolithic France to tribal Africa, trepanation emerged as a universal response to head trauma, epilepsy, or even spiritual ailments. Perhaps they observed how head injuries sometimes improved after bone fragments worked loose, or maybe they believed releasing evil spirits could cure madness. Either way, their empirical methods forged a path that modern medicine would retrace centuries later, proving that the line between ancient intuition and modern science is thinner than the blade of an obsidian scalpel. Standing in a museum today, staring at a skull with a carefully healed hole, you're left with a humbling thought. Beneath all our technology, the human drive to heal and the courage to let someone open our skulls in the attempt hasn't changed at all. The scalpel's shape evolved, but the healer's hands still tremble with the same hope. At the heart of ancient Hindu cosmology lies a vision so vast it makes our modern telescopes seem like toys, a universe that breathes. The Rig Veda, composed over 3,000 years ago, doesn't just describe a single creation event. It speaks of endless cycles of birth, destruction, and rebirth, where entire universes expand and collapse like the lungs of a cosmic giant. The Sanskrit term for this concept, kalpa, stretches time beyond comprehension. one cycle lasts 4.32 billion years, eerily close to our current estimate of Earth's age. But what's truly staggering isn't just the scale, it's how closely these millennia-old ideas align with cutting-edge physics. Take the Big Bounce theory, a modern alternative to the Big Bang. Proposed by loop quantum gravity physicists, it suggests our universe didn't emerge from nothingness but rebounded from a previous collapse, echoing the Hindu concept of pralaya, the periodic dissolution of all matter. Both describe an eternal dance of contraction and expansion, where each universe inherits traces of the last. The parallels grow stranger when you examine details. Vedic texts describe cosmic seeds, bijas, carrying information between cycles, while quantum theorists now ponder whether black holes preserve data from prior universes as holographic imprints. String theory takes this further. The Mahabharata's descriptions of layered realities, multiple worlds stacked like fibers in a rope, uncannily resemble the multiverse hypotheses of physicists like Brian Greene. Ancient seers spoke of lokas, parallel dimensions inhabited by beings of different vibrational frequencies. Compare this to string theory's 10 or 11 dimensions, where particles are tiny vibrating strings and matter's properties depend on their resonance. Even the Bhagavata Purana's assertion that countless universes float like atoms in a cosmic ocean mirrors physicist Andrei Lin's eternal inflation model, where bubble universes continually spawn in an infinite meta-universe. The most profound connection isn't in the math but the metaphysics. Hindu cosmology views time as cyclical, not linear, a wheel turning through 4 yugas or epochs. Modern physics, grappling with entropy and the arrow of time, now toys with similar ideas. Nobel laureate Roger Penrose's conformal cyclic cosmology proposes that the universe's distant future, a cold, empty expanse of photons, could become the low-entropy starting point for the next cycle, blurring the line between end and beginning. It's as if ancient rishis intuited what particle accelerators now probe. That creation isn't a one-time event, but a refrain in an infinite song. What's haunting isn't just the accuracy of these predictions, but how they were conceived. Without telescopes or equations, Vedic seers used deep meditation to perceive reality science is still unraveling. Their descriptions, like the golden womb, Hiranyagarbha, containing all potentiality, resonate with quantum vacuum fluctuations where particles blink in and out of existence. Whether this is coincidence, forgotten knowledge, or a testament to human intuition's power remains a mystery. But one thing is clear: when ancient hymns whisper of universes pulsing to the rhythm of cosmic breath, they're not just spinning myths. They're mapping the deepest rhythms of existence, ones we're only beginning to hear. Strolling through the ruins of a Roman villa, you might notice something peculiar beneath your feet: raised brick pillars spaced evenly across the floor, their surfaces blackened by centuries of soot. This isn't just debris, it's the skeleton of a hypocaust system, the world's first central heating network, built over 2,000 years ago. Far from primitive, these underfloor labyrinths of hot air channels were so effective they inspired the radiant heating systems we use today. Proof that Roman engineering wasn't just grand, it was downright cozy. At its core, the hypocaust was a masterpiece of thermodynamics. Slaves or servants would stoke furnaces in an external chamber, heating air that then circulated through the hollow space beneath raised floors, supported by those stacks of brick pillars. The heat would rise evenly, warming marble or tile floors that retained temperature like modern thermal mass materials, but the Romans didn't stop at floors. Walls were often lined with clay pipes or hollow bricks called tubuli, turning entire rooms into heat radiators. The baths of Caracalla, for instance, could maintain a steamy 80 degrees Fahrenheit in winter, comfort levels that rival modern spas despite soaring vaulted ceilings that would normally let heat escape. What's astonishing isn't just the scale of these systems, but their sophistication. Archaeologists at Pompeii found hypocausts with adjustable flues, allowing precise temperature control in different rooms, a concept now standard in zoned heating. The Romans even understood airflow dynamics. The slope of floors and placement of vents created convection currents that distributed heat without fans or pumps. In Britain's Fishbourne Palace, engineers discovered a hypocaust that alternated hot and warm zones, mimicking modern underfloor heating grids that prevent overheating. Fast forward to today, and the DNA of hypocausts lives on. Modern radiant heating systems swap wood-fired furnaces for electric coils or hydronic pipes, but the principle remains identical. Heat from below, let it rise gently, and let thermal mass do the rest. Even the terminology nods to antiquity. The word hypocaust literally means heat from below in Greek. The Romans just did it without plastics or microprocessors, relying on gravity, masonry, and a deep understanding of physics we often assume are modern insights. But here's the twist: in some ways their system was superior. Unlike forced air heating that dries out air and circulates dust, hypocausts provided steady, humid warmth ideal for respiratory health. Contemporary studies show radiant heat reduces allergens and energy use by up to 30%, exactly the efficiencies Roman architects achieved. Luxury homes from Dubai to Norway now replicate this approach with heated floors and walls that echo the baths of antiquity. The real lesson of the hypocaust isn't just about engineering, it's about mindset. The Romans didn't see comfort as a luxury. They viewed it as a solvable problem, blending physics, art, and social design. Walking on those warm floors, they weren't just heating stones. They were laying the groundwork for a philosophy that still warms us today. That technology should serve human dignity, quietly and without fuss, whether you're a toga-clad senator or a modern homeowner in slippers. For centuries, European sailors clung to coastlines, terrified of the open ocean's vast emptiness. Meanwhile, Polynesian voyagers were crisscrossing the Pacific, navigating thousands of miles between pinprick islands with nothing but the stars, the waves, and their own finely tuned intuition. At the heart of this astonishing skill lay the Maori star compass, a mental map of the heavens so precise it functioned like a celestial GPS. Unlike Western compasses that fixate on magnetic north, these star paths were dynamic, dividing the horizon into 32 directional houses, each anchored by a rising or setting star. But the true genius wasn't just memorizing positions. It was reading the living ocean itself as a navigational instrument. Take the technique called tilapa, flashes of underwater lightning. Maori navigators observed how these brief streaks of bioluminescence, caused by distant island disturbances, radiated through the ocean in straight lines, pointing unerringly toward land sometimes hundreds of miles away. They paired this with wave piloting, detecting subtle deflections in swells as they bounced off unseen shores. A trained navigator could feel these shifts through the hull of a canoe, interpreting the sea's texture like braille. Cloud formations, bird flight paths, even the taste of seawater all became data points in an ancient algorithm of wayfinding. Modern science has only recently caught up to this wisdom. In the 1970s, the legendary Hokulea voyage proved the system's accuracy by sailing from Hawaii to Tahiti without instruments, guided solely by traditional methods. Satellite studies now confirm what Polynesians knew. Ocean swells refract around islands in predictable arcs, while specific stars like Hikionalia Spica and Ki Ali Okona I Kalua's Southern Cross align with key Polynesian trade routes. Even the star compass's structure mirrors astrophysical reality. Its divisions correspond to the Earth's axial tilt and the ecliptic plane, concepts Western astronomy formalized millennia later. What's truly revolutionary is how these techniques are resurfacing today. Amid climate crisis, voyagers like the Polynesian Voyaging Society are reviving star compass navigation to reduce reliance on fossil-fueled shipping. Solar-powered canoes now ply Pacific routes their ancestors charted, using renewable knowledge as literally as renewable energy. Universities from Auckland to Berkeley study these methods not as historical curiosities, but as blueprints for sustainable transport, a fusion of ancient intuition and modern environmentalism. The Maori star compass doesn't just guide canoes, it recalibrates our entire understanding of technology. In an era of satellite overdependence, it reminds us that the sharpest navigation tools might not be in our pockets, but overhead in the night sky and beneath us in the whispering waves, waiting to be read by anyone willing to learn the ocean's language. From the celestial calculations of the Mayans to the self-healing concrete of the Romans, these 25 ancient predictions reveal something extraordinary. Human ingenuity isn't a straight line, but a spiral looping back to ideas we thought were brand new. Every gear in the Antikythera Mechanism, every shimmering nanoparticle in the Lycurgus cup, every star chart etched into Polynesian memory whispers the same truth. Our ancestors weren't just stumbling in the dark. They were solving problems with tools we're only now beginning to rediscover. So here's the haunting question. If these civilizations could envision helicopters, batteries, and even programmable computers millennia before their time, what else might they have known? How many more breakthroughs were lost to war, decay, or the simple erosion of time? The Baghdad Batteries hint at experiments with electricity. The Nazca Lines tease the possibility of aerial navigation. The Vimana texts suggest flight beyond our current understanding. Each artifact is a breadcrumb leading us down a path we've barely begun to explore. This isn't just about marveling at the past, it's about redefining what's possible. If the Greeks could harness steam and the Chinese could weaponize chemistry, what other fragments of forgotten knowledge might be hidden in plain sight? Maybe the answers are buried in unread manuscripts waiting for a fresh pair of eyes. Or perhaps they're encoded in myths we've dismissed as mere stories, their truths masquerading as metaphor. Now it's your turn. Which of these ancient predictions left you awestruck? Was it the surgical precision of trepanation, the eerie accuracy of Zhang Heng's earthquake detector, or something we didn't even cover? Drop your favorite example in the comments. Let's unravel these mysteries together. And if you're hungry for more deep dives into history's hidden corners, hit subscribe. The past isn't done surprising us yet. Who knows, the next discovery might rewrite everything we thought we knew.